All right, there's a couple of things that I'd like to review with you as far as assigning oxidation numbers. If we look at the first question here, so 1A, we've got H2SO2. Based on the rules that you've learned, you know that oxygen and hydrogen are pretty much always going to be +1 and -2. There are some exceptions for this, but for all of the molecules that we will see, hydrogen is +1 and oxygen is -2. And so what that leaves us with is we have to figure out what sulfur is. And so what I've done here is, in this line right here, I've made an equation that says the 0 refers to the overall charge on H2SO2. It's neutrally charged, it has no charge, hence the 0. The 2 right there is for, there are 2 hydrogens and each one of them have an oxidation number of +1. The X represents the oxidation number of sulfur, and then the 2 times -2 is just 2 times the oxidation number of oxygen, which is -2, and the reason it's 2 is because there are 2 oxygens in the compound. And so if we simplify that in the next line, right here we see that we have 0 equals 2 plus x minus 4, and we end up with x equals +2. So the x is equal to 2, or the 2, the positive 2, is the oxidation number for sulfur. One strategy for assigning oxidation numbers for ionic compounds is to just split the compound into its component ions. So I have Ca2 plus and OH minus in this, in calcium hydroxide. Right away then I know that the oxidation number for the calcium is +2 because it's equal to the charge on the monoatomic ion. And then again I have oxygen and hydrogen, and they are just -2 and +1. And just to show a quick check, I'm going to take the oxidation numbers and add them up, taking into consideration the number of each type of element. And so I've got 1 calcium at +2, I've got 2 oxygens at -2, and 2 hydrogens that should be +1 in there. And all of that adds up to 0, which is equivalent to the charge, the total charge on the calcium hydroxide. And I use the same sort of strategies in C and D to find the oxidation numbers for each of those elements. In E, just a slight variation. So again, I split it into the ions that it's made of, so the Na1 plus ion and the PO43 minus. So that tells me that sodium has an oxidation state of +1. We know that oxygen is -2, so we have to figure out phosphorus. So instead of looking at the entire compound, I could just figure it out using just the phosphate ion. And so if X is so if this X right here is the oxidation state for phosphorus, I know that my oxygen, I've got 4 of them, and they're each -2, and all of that has to add up to -3, which is the charge on the phosphate ion. And so just simplifying for that, I get X equals to -5, which is the oxidation number for phosphorus in this. And in part F, do the exact same thing, just kind of do it twice. And so this number that's cut off here should be -2. And I solve for both I don't know the nitrogen and don't know the sulfur, so I solve for X to get the nitrogen, solve for Y to get the sulfur, and right down below here is my set of oxidation states for each of the elements in that compound. So before being able to write the half reactions as it asks, we need to determine if the reaction is in fact is in fact a redox reaction. And in order to do that, the first thing I say to do is to assign oxidation numbers to each of the elements, because once you do that, if you see that the oxidation numbers change in going from reactants to products, so for instance carbon is a -4 here and a +4 here, I see that that oxidation number has changed. That tells me that since the oxidation number has increased, i.e. gone from -4 to +4, carbon has been oxidized. That oxidation number has become more positive. Whereas in the case of oxygen, it's gone from being 0 to being -2. I see that the the number has gone down, or it's reduced in value, which is a sign that that element has been reduced. And so therefore I have something being oxidized, something being reduced. I could write oxidation and reduction half reactions for each one of those. However, I'm not going to in this case, because there are a couple of more steps that we don't need to worry about in this course that you would do to write those half reactions. So we'll take a look at some of the other reactions and their half reactions. Okay, so for part B here, we see that what I've done is assign the oxidation numbers, and anything in its elemental form, i.e. both magnesium and chlorine in this case, has an oxidation state of 0. But now in this compound, we have magnesium having the oxidation state of +2 and chlorine having the oxidation state of -1. And that kind of makes sense in that if we connect to the electronegativity values, that chlorine is the more electronegative element. It's going to be gaining the charge there. It's going to be it'll have the negative oxidation number. But I think the better way to look at this in the case of magnesium chloride being an ionic compound is that each of the ions, the charge on each one of those ions is the same as their oxidation numbers. And so we can see that magnesium is going from being 0 to +2, and chlorine is going 0 to -1. And so the value for chlorine has been reduced, hence I can write it in the reduction half reaction. And I just take the elements, so I take Cl2 and I've got Cl- on this side, and I write the balanced half reaction. Now notice that I need to include the electrons. That is what in a half reaction you show electrons, whereas in a full balanced equation for a reaction you don't show the electrons. And the reason I have 2 electrons is because on this side of the equation I have 2 units of negative charge, 2 negatives, and so I need to have an equal number of negatives on the other side of the reaction, and so I need to add 2 electrons like I did here. And so overall this equation is balanced for charge. There is 2 units of negative charge on the reactant side, and there are 2 units of negative charge over here, as well as 2 Cl's, 2 Cl atoms, and 2 Cl atoms. The other big thing to come out of this is that in looking at the oxidation half reaction, the number of electrons that are being lost right here in the oxidation half reaction is equal to the number of electrons that were gained by the chlorine in the reduction half reaction. And that is always the case in a redox reaction. The number of electrons lost has to be equal to the number of electrons gained, because electrons can't just come from nowhere or come out of nowhere. They have to come from somewhere and they have to go somewhere. And the final thing in looking at this, these 2 half reactions, is that for a reduction half reaction, you'll always see the electrons on the reactant side. So they're always on this side of the equation because electrons are being gained in a reduction process. Whereas in an oxidation half reaction, you'll always see the electrons on the product side, or on the right-hand side, and that's because electrons are always being lost in an oxidation process. For part C here, we see that after assigning oxidation numbers to each one of the elements, we see that none of the oxidation numbers have changed in moving from reactants to products. So what I mean by that is the oxidation number for calcium is +2 here and it's +2 here, just like for phosphorus, for example, it's +5 and +5, or the nitrogen was +5 and +5. So the oxidation numbers don't change. That means that there aren't any electrons that have moved around, and you do not have any sort of a redox process taking place there. Without going into as much detail as I did up above, one other approach I want you to see for a reaction like we see in part D is that really what we're interested in is the total ionic equation, or even the net ionic equation, as we see here in in part E. Focusing on part D though, I write the total ionic equation, and the NH4 plus is the same on both sides of the equation. I have two NH4 plus, and presumably they'd be in the same state. Those things aren't, the NH4 pluses or the ammonium ions aren't involved in the reaction. And so I can write, I can simplify the process of writing my half reactions by leaving out the ammonium ions, which are the spectator ions. And so from that, I get my reduction half reaction right here and my oxidation half reaction right here, and I only write the elements that are either being reduced or oxidized. And if we look at part E, we take it kind of one step further, or I see that here you've got your total ionic equation, but let's simplify that and remove the spectator ions because we have the 3 SO4 2 minuses on both sides of the equation. We remove them to get the net ionic equation, and from that we can see that the Mg is going from having an oxidation state of 0 to an oxidation state of +2, so therefore it must be oxidized. That's why it's written in the oxidation half reaction. Likewise, the iron is going from +3 to 0, so its oxidation number is going down or being reduced, so it is involved in the reduction half reaction. And I write my balanced half reactions using the appropriate number of each of the atoms or ions involved, as seen in both the total and net ionic equations. And then the key thing is that I have 6 electrons here because I have 2 times 3 plus, right? I have 2 things that have a charge of 3 plus, and so that's 6 positives. And so I need to have 6 negatives in order to have a total charge of 0 on this side of the reaction. And I know the total charge needs to be 0 on the reactant side because it is the product side has a total charge of 0. And again, note that there are 6 electrons involved in the reduction half reaction and 6 electrons involved in the oxidation half reaction, because the number of electrons always have to be the same, and it works out that you need 6 electrons for both reactions in order to balance each of those half reactions.